Hello everyone. Good. Okay. So I guess you can hear me. Yes, you're answering. Good. Um, how's the face-to-face marking? Is everyone already doing that? I hope you're not missing your appointments for that. Okay. So today we'll keep talking about ray tracing, of course, right? We still have a lot of things to discuss. And we will actually discuss a couple of things that people already asked on Piazza, and on purpose I was not answering a couple of things because I didn't want to like spoil, right? Like give you spoilers from today's lecture. So let me just, yeah. Okay, can you see my screen? I'm sharing my screen. Good. Okay, so we have 42 people, which is great. So learning goals for today. We will talk about ray triangle intersection. That is basically the thing that it was, I mean, we almost discussed that on last lecture, but there's a tiny detail that we need to discuss. We will talk about ray depth, depth buffer, and finally also anti-aliasing, right? Okay, so let's see this. We were saying that in order to get the ray triangle intersection, we were discussing, okay, what is basically the solution. And the solution is we first compute the intersection to the plane, right? We already have the formulas and equations for that. And then we can compute the barycentric coordinates. So remember, the barycentric coordinates of this point, right? If it's on the same plane of the triangle, and if it's inside the triangle, right, they must be almost equal to 1. And I think someone was already asking that, like, what happens if my barycentric coordinate is not exactly 1, right? It's just a little bit above 1 or things like that. Remember that I've told you already that when you're implementing stuff in computer graphics, because we are using float numbers, right? I mean, getting a number that is exactly 0, right, or exactly 1 is usually very hard, right? Sometimes it's even impossible. So you don't compute your barycentric coordinates and then just add the barycentric coordinates and have like if, right, if the sum of barycentric coordinates is equal to 1.0, because that probably will never happen, right? So what you usually do is you can create a variable. We usually call them epsilon, right? Like a very, very tiny variable. What do we assume for epsilon? Yes, well, okay, yeah, that's it. That's the thing, right? So you can assume as epsilon maybe like 0.001 or something like that. And yeah, so you just compare, right? You compare the difference between 1 and your and the sum of your barycentric coordinates if that if the difference is less than epsilon, right? And do we have general standard for epsilon? Good question. Not that I remember. Actually, I've used, I mean, in general in computer graphics, I think I've used different epsilons depending on the project, depending of what is the thing you are measuring. So I remember, for example, this also happens when you're checking, for example, angles between vectors, right? And if you're dealing with mesh algorithms, that's the type of thing that I do. If you know your mesh already and you know that you will never have triangles with like very, very small angles, right? Maybe your epsilon can be, yeah, a bit larger. Yeah, depends on the data. I think in general, yeah, 0.001 I think it's a good epsilon, but yeah, as far as I remember, there's no standard for that. Yeah, so this is important, right? So because one is the geometrical intuition of this type of methods and also like the formulas that we see, and the other is how you literally implement it, right? So if you're like doing like that and you want to compare it to have it exactly 1, you might miss a couple of intersections, right? Because maybe the floating numbers will trick you. Okay, so I guess this is very clear, right? We have a ray, we have a plane from which we have a point in the plane, and also we have the normal. If what we have is a triangle, remember we get the normal, right? By taking the cross product between any two vectors from this guy. The order of the cross product is important. Remember, in computer graphics in general, and I discussed this when we talk about custom meshes. In computer graphics, we always use the right hand rule to create the triangles, right? So if this is, I don't know, A, B, C, if this is the order, right, it means that the normal is on this side, right? So you take, in that case, for example, if it's A, B, C, you take the cross product between A, B, and A, C, right? And you will get this normal. And any point of the triangle is obviously a point in the plane, right? So you have that, you compute the intersection with the plane, and then you get the bicentric coordinates. So my question for you is, and please, if you already saw the slides, don't spoil. Do you spot any problem with this method? I mean, I think some people already noticed something, and you were asking on Piazza, but again, I didn't answer because it was, yeah, spoiler. Did you notice any, or you spot any problem with this method or the formulas that I give you? Okay, I guess nobody's answering. Let's see something. This is the formula I gave you for getting the Ray plane intersection, right? So a couple of people already spot something here. Okay, so someone is saying, can we tell if the ray is not hitting the triangle? Okay, what do you mean by that? Do you mean that the ray is on the same plane than the triangle? Or same as for the sphere? Okay, ray misses the sphere. Well, that we already discussed, right? In the case of the sphere, remember that you compute the distance d, right? Which is basically the distance from the center of the sphere to the ray. If that distance is larger than the radius of the sphere, it means that you basically missed the sphere. If it's equal or less than the radius of the sphere, it means that you are for sure hitting the sphere. So in this case, the way you check if you're missing the triangle is with the barycentric coordinates, right? But first you need to compute the intersection with the plane. So once you have the intersection in the plane, the way you know if you're missing the triangle is by taking the barycentric coordinates and compare if they are close to 1 or basically equal to 1, right? But there's something here that a couple of people were asking about these formulas, and I think we even discussed a little bit the other day. Give me a second. So, another question. In which cases do you think the ratio k, remember k is a ratio, right? K is the ratio between A and B, right? Basically, that is like a scalar value for R, right? Because I'm taking R, I'm multiplying by this scalar variable or this ratio, and then I just add the origin of the camera or the origin of the ray. So in which cases do you think the ratio will be negative? What do you think? Okay, someone says the triangle lies opposite to the direction of R. Yes. So notice that A or B can be negative, right? Again, someone already told us that the other day, right? And someone already posted something like that on Piazza, right? Okay, but what happened if my numbers are negative, right? Of course, because we have a dot product, depending on the direction of this vectors right here, W and N and R and N, these guys can be negative, right? The thing is, if these guys are negative, imagine that both are negative, right? And we have, I don't know, 130. Minus 100 over minus 30, in the end I have a positive ratio, right? The thing is, I want the ratio. But yeah, but that is true. The thing is, depending on where is the plane and where is the origin of the ray, you can have a negative value when an object is basically behind the origin of the ray. Do you agree with that? Good. So what do you think? Is that a problem? Because the thing is, we know that the general concept of ray tracing is that for every pixel on my image, I need to cast a ray, right? But that ray needs to basically iterate every object on the scene, right? So what happens with objects that are basically behind the camera? Because right now the formulas we have, they basically will give you, if you iterate, for example, this object right here, and you use exactly the same formula, you will get the intersection from this ray. You will basically get this point right here. The formula will not prevent you to get this point right here. So basically, the direction of the ray is kind of meaningless in those formulas. And someone is asking, do we care about objects behind the camera anyway? It's a very good question, right? It's like, yeah, I mean, why, what do we do, right, with this type of things? So there are kind of different answers. So that is the type of things that we will discuss today. So let's see something. The thing is, in general, or in practice and in general, we never test objects that are in the back of a ray. Okay, and someone is already saying, aren't objects behind the camera discarded as is not in the frustum? Yes, exactly. That's the type of things that I want to discuss with you today, and for you to think about this, right? So there are a couple of things. Let's see this thing first. If we have imagine that we have a scene with 1 million spheres or 1 million triangles, right? And again, we need to we say that for every pixel on the image plane, we need to create a single ray, and that ray needs to basically iterate for every object in the scene, right? To see if it's hitting something. Imagine that you have, again, 1 million triangles or 1 million spheres, and maybe 90% of those spheres are not even close to this ray. There may be only 2 spheres that will probably touch that ray, and everything else they're not touching. Right? That will be incredibly inefficient. Do you agree? It will be very, very hard, right? So the thing is, in practice, we accelerate the ray tracing algorithm or the ray tracing process by using space partition algorithms. This is a very lame version of this. It's just like an schematic view of this. But what we do is we basically take the space, the entire 3D space, and we fragment that space, right, in chunks. You can use oak trees or something. I mean, in general, you can use you can use oak trees, but we usually use a more adaptive space partition algorithms like KD trees. We will talk about that later. Actually, we will have a lecture about accelerating techniques for ray tracing. But basically, what we do is we segment our space, right, in pieces. So we always cast, or we always only iterate objects for each ray. Objects that are basically on its way, right? So for example, in this case, we will never iterate this object. We will never iterate this one because we are only iterating with objects that are basically on these tiny spaces, right? And basically on the walk, on the path of the ray, right? And someone is saying this is the same technique as collision detection, I think. Yes, for collision, not exactly the same, but yes, very similar. For collision detection, yes, it's the same. So basically the problem, I mean, algorithmically speaking, when you have what you are asking is, collision detection is something that happens, for example, in video games. You want, I don't know, you're throwing an object and you need to, I don't know, simulate that object is basically like colliding with a wall, and you might need that for simulated physics, for example, right? So the thing is, if eventually what you have is you have an object, let's talk about spheres, right? You have 2 spheres and you want to, if you want to know if they are, collisioning or not, right? What you need for each object for each position in space, you need to compute the closest points in space to that position, right? And yeah, that's true. The type of algorithms you will need to compute that in a very efficient way is a space partition algorithms as oak trees or KD trees. Again, I think the better is probably KD3, and yeah. So that's one important thing, right? So in general in ray tracing, for every ray that you throw, if you are using the correct accelerating algorithm and you are using space partition algorithms, you will never ask the ray to hit something that is basically behind it. Okay, that is the first thing. Is this clear? Okay, and someone is asking, give me a second because I'm seeing a lot of questions on the chat. Give me something. Okay, and someone is saying, but objects behind the ray can still cast shadows. Yes, very good question. Of course, we still need those objects, right? If maybe they're still casting shadows, and it's not only for shadows. Very good question. It's not only for shadows, but also for reflection, right? But the thing is, when you're computing the rays, for example, the rays for checking shadows, imagine that I'm throwing a new ray from this position on this direction, right? And then I hit this object, right? And let's imagine that once I hit the floor, right? If I need to check if that object or that pixel in particular is under shadow or not, I need to throw another ray, a secondary ray. And then I need to throw that ray now in direction of the light, right? The thing is, for that secondary ray, you will also use your space partition algorithm, and you will never check things that are behind that, right? The thing is, for every ray, basically the rule here is we will never use objects that are behind the ray. So it doesn't matter if it's a secondary ray now checking the light. For that ray, now you will never check something that is behind that ray, right? Okay, the thing is, so that basically will never happen, right? You will never check objects that are behind the ray. It doesn't matter if it's a primary ray that is coming from the camera, or if it's a secondary ray that is, for example, checking shadows, right? You will never check something that is behind. What can happen also is, look at this object here. These objects are representing closed meshes, right? So if you have closed meshes, like this object right here, usually the intersection happens in the part of the object that has basically its normals on the like pointing into the opposite direction to your ray. Do you agree? Because basically, if I have this sphere, my ray basically intersects the sphere in 2 points, this one and this one, right? But because this is a closed object, I will get the one that is basically like closer to me. You agree? The thing is, sometimes we have open objects or open meshes. That is also something very common in 3D or in computer graphics. Is not all objects are basically closed meshes. So if you have an open mesh, imagine that you have a plane here, right? That is an open mesh, or whatever, maybe a surface that is an open mesh. Sometimes we're seeing that open mesh from a certain direction in which all its normals are pointing to the camera, but sometimes we're seeing the back face triangles, right? Do you agree? We even have a specific stage on the rendering pipeline to decide if we want to render back face normals or not, right? Usually, if we are talking about now I'm not talking about ray tracing, I'm getting back a little bit to real-time rendering. In real-time rendering, if you have closed meshes and you activate the culling process, remember, culling will check the normal of the faces, and if those faces are basically like going onto the opposite direction from the camera, right, like looking back to the direction of the camera, we will basically discard those triangles. However, you can have open objects, right, from which maybe you want to render the back face. So a very good example of that is a flag, right? So imagine something like this, like a flag, the mesh of this flag is obviously open, right? You have one side of the flag will have all its triangles, right, basically pointing out of my monitor, and the other, right, the other side of this flag is basically is a back face, right? There are back faces, right? The thing is, if you have a flag in a video game, you obviously want to render the flag from both sides because sometimes the camera can be on the other side. So this is also happening in ray tracing. So that's why that formula is the formula that we have is very good, because you will always get the intersection. So it doesn't matter if the normal is pointing, if the normal of the mesh is basically pointing to one side or the other. What you can do is, depending on your requirements, depending on the type of material you want to show, if you want to not render back face, if you don't want to render basically back faces, once you get the intersection, you can check the normal, and if it's a back face and you don't want to render back faces, that's perfectly fine. You just don't take that into account to get the pixel color, right? But if it's something like this, like a flag, and your camera is basically behind the flag and you want to render the flag, that is perfectly fine. You get the intersection first, and maybe it doesn't matter for you. You want to render both sides, that's perfectly fine. You just compute the color, right? So that is, remember, something that is optional, right? Okay. Questions from this? Yes, I have
Hey.
Hey.
So just back to the flag example. I don't know if I have the correct impression, but it is the rendering both front and back required because the flag's alpha value is sometimes less than 1. Is that what you're referring to?
No. I'm not talking about alpha. Alpha values, remember, the alpha values are define the level of opacity of a material, right?
Right.
Alpha depends if something is transparent. Now, what I'm saying here is, imagine the mesh of this flag.
Right.
You have this will be an open mesh, right?
Mm-hmm.
So because it is an open mesh, it means that if that mesh is properly created, right? All the normals of the triangles of this mesh are either pointing on this side or maybe the other side, right?
Yeah.
If everything is unified. But if you do the back face culling, it means that maybe you have the camera on this direction and you see the flag, but then suddenly, because it's a video game or whatever, right? Maybe you even have a simulation of this flag and the wind is blowing, right? So maybe the wind blows and then you are starting to see the other side of the flag. If you do back face culling, basically the flag will disappear, right?
Yep.
Because now you're seeing the back of the flag, right? So that's the thing. I mean, not every object. We don't want to apply backface culling for every object. Sometimes we want to render two-sided objects, right? And this is a very good example, a flag, right? Because the other option is, instead of having an open mesh for a flag, the other option is basically to create a closed mesh for a flag. But that will be basically, like literally, to duplicate the number of triangles, right? So imagine that I take the 3D model of the flag, and I literally there's a process for that, and it's called shelling. Let me show you that very quickly. Give me a second. Give me 1 minute. Yes, and someone else is asking, does open mesh just mean meshes that we need to render from all sides? Again, depending. Maybe you want to do, if you want to perform back culling, if you don't want to compute or to render the back part of something, but sometimes you want, right? Okay, so let's imagine something. We'll create, maybe having a real example will be better. So this will be basically something like a flag. So this is obviously a mesh with whatever amount of whatever amount of triangles, or in this case are quads, right? I can even maybe I can apply okay, maybe 4 and 4, and the proportion is incorrect, so let's turn this guy. Okay, so this is something like a flag, right? So if I ask Tree Studio Max, I go to Object Properties, I can ask Tree Studio Max to do the back face culling, right? So I can say back face cull, right? It means that if I am seeing the flag from this side, it's perfectly fine. But if I see the flag from the other side, basically the flag disappears, right? So in the case of a flag, right, this is something that you don't want this, right? You don't want your flag to disappear if suddenly the wind is coming to the other side, right? So there are basically two options, right? When you define the material of this flag, so let's say that this is a red flag, right? So one option is to define your material as a double-sided material. It means that whenever this material will be rendered, back face will not be applied, right? That's it. So, or if we are talking about ray tracing, right? I mean, this is Tree Studio Max, but basically, if we are talking about ray tracing for that argument in particular, if you hit the triangles, right, with your ray tracing, and you check the normal, and the normal is basically pointing to the other side, you don't care, right? You maybe don't even check the normal, right? Because you want to render the flag from both sides. So that is one option, right? Just don't apply the back facing, the back face culling. The other option is you get an open mesh and you modify the mesh to make it a closed mesh, but that is an overkill. What is that? What do I mean with that? I can get the mesh and I can apply a process called shelling, which is this. Basically, I can, right? Like, it's like making an offset. So now I have an object that is a closed mesh. Obviously, it had both sides, right? So there are no back face things anymore, right? And it could be very, I don't know, whatever. I mean, very, very tiny. But this is an overkill, right? Because I'm more than duplicating the number of triangles. So it's just easier to not process back culling with a type of things like this, right? But then sometimes you can have open meshes that you don't want to use. That you don't want to render as a double sided. For example, usually the floor of something. Imagine that you are playing video games, right? And you're creating a video game. Well, every video game scenery will have a floor, right? And the floor can be just a regular plane, or you can have mountains or whatever, right? Usually, the floor on a video game will be an open mesh, right? It doesn't matter if it's a mountain or whatever, right? The mountain in a video game will be an open mesh, but you don't want to see the back face for that mountain because your camera will never be on the other side. So for that case in particular, you want to process the back face calling for a mountain, right? But not for a flag, right? Okay, let me see if you have more questions. Check quickly. And someone, but the camera can move to the other side of a closed mesh as well, like a sphere. Yes, of course. Yes. Don't really get the difference between open and closed mesh. Oh, okay, if you don't know, okay, let me check. So you don't understand the difference between open and closed meshes. This is a closed mesh. There are no borders on this mesh. There are no holes or borders on this mesh. If I, for example, make this thing to, if I can make this as an editable poly, and I get some of its triangles, and I erase those triangles, now I have a border, right? So this is an open mesh. This is an example of an open mesh, right? And because it's an open mesh, I can, for example, right now, trees to the max doesn't perform. It doesn't perform back face culling by default. You need to activate or deactivate it. So I can go project properties and I said back face cull. So now the inner part of the object, because it's open, right? The faces here, it's normal. It's basically back facing the camera. So, and because apply back facing culling, they're discarded on the rendering. So I'm not able to see those, right? So basically they're transparent, right? So this is an open mesh, right? And again, one option, if you want to render an open mesh, one option is to just treat that as a double-sided, right? So you will render whatever fragment or intersection between rays with that object. It doesn't matter if it's back face or not. Or you apply this, again, this very horrible technique of just like shelling your object, right? That is like duplicating your mesh and give like a bit offset, right? I mean, sometimes we use this technique, but not for this particular example, right? Okay, so is that clear? Is now clear the difference between open meshes and closed meshes? And someone is saying how the flag is an open mesh. Well, the flag is an open mesh because it's a plane, right? So again, if I remove the shell, and actually I will remove most of the, yeah, so look at like this, right? Every give me a second, I will convert to editable poly, and I will, because these are quads, so maybe it's better for you if I show you triangles. Okay, so here we have, this is a mesh, we have triangles, right? Every triangle here has its normal pointing in the direction of my monitor right now, right? You agree? It means that the back side of each triangle, it's a back face, right? So if I apply the back face culling, that's why they disappear. So that's what, yeah, this is an open mesh, right? It has borders, right? Actually, I can in Trees to the Max, you can select the vertices of a mesh, the edges of a mesh, right? And you can also, let me change the color to this guy because it will be harder to see. Give me a second. Let me just make it gray. You can select this object and you can select the border. And can you see? It's like the red, right? So these edges right here, the collection of these edges this is basically the border, right? Inherently speaking, a closed mesh don't have borders. They don't have borders. Okay, good. So let's continue. Okay, someone's saying, can we say open mesh plus shell is equal to closed mesh? Yes, of course. But again, shelling an object, for example, shelling the flag just because you want to like see the flag from both sides, that is a horrible overkill, right? You're literally more than duplicating your triangles. Okay, so now again, let's keep talking about ray tracing. Let's talk about objects behind the camera. So someone was already asking, okay, do we even care about objects that are behind the camera? And maybe this could be something that you can ask. And again, I think someone already asked this on Piazza. I'm not sure, but someone did ask this on this lecture, right? Could we just do a frustum clipping to accelerate the process? That could be a good idea, right? I mean, in real-time rendering, that is what we do. We get the frustum, right, and we apply the perspective projection to basically distort everything that is on this perspective frustum. We distort everything to fit in the NDC cube, and once if it's on the cube, we can just clip, right, cut everything or discard everything that is outside basically the visible volume from the camera. We all know that, right? So why we can't do this on ray tracing? Because ray tracing, we can have reflective materials. So if every material here it's reflective, we have the camera here, we throw a ray, we hit this point right here, and because this guy is reflective, it needs to send a secondary ray that is coming in this direction, and now it needs to get into this guy here. This guy is behind the camera. Here I'm not breaking the rule that I told you before, because I told you before we never process objects that are behind the ray. I'm not breaking the rule here because this object right here is behind the first ray, so I will never check this guy for the first ray, but it's in front the second ray, right? So for example, for the second ray, I will never check this guy. I need to check every guy that is basically from this point in this direction, right? So then I get to this guy, but this guy is also reflective. So now I need to cast another secondary ray now in this direction, in the reflection vector that is coming into this direction. And now it hits this one, right? So you're basically there hitting everywhere, right? And okay, sorry, I'm reading a question. Why did the inner quads of a spherical mesh disappear earlier and not the outer quads, basically? I don't understand your question. What? Oh, well, when I got the sphere and I removed the, if you talking about that, I got the sphere and I removed the top part. They didn't disappear before, or at that time they didn't disappear because 3D Studio Max don't apply face culling by default. But also face culling is a property, is not a global property in 3D Studio Max. In 3D Studio Max, it's a property, it's a local property for every object. So before I applied the back face culling exclusively on the flag, so that's why the flag had this back face culling. But when I created the second object, the sphere, that sphere didn't have that local property of back face culling. Yeah, that's why it was not, they didn't disappear. I had to right click, go to properties, and ask 3D Studio Max for that object in particular to do the back face culling, right? Okay, so that is why, right? This is why we can do frustum culling, because if we are doing, I mean, if you know for sure that you will never use reflective rays, right? That every object in your city is probably not reflective. You might accelerate the process, right, by maybe performing clipping, right? But the thing is, because you will also use space partition algorithms, right? I mean, it's almost the same, right? If you're not processing these space areas, right? Only the space. If you're only processing the space areas in which every ray is traveling, you don't need to clip anyway, right? So yeah, so we almost never discard objects in the scene, right? Because we might need it to perform reflections, right? Well, now we can have another problem that again someone already posted on Piazza, and I didn't want to answer because I was going to discuss this today. The thing is, imagine something like this, right? So we have a ray, right? So this guy is reflective. So now we need to cast a secondary ray. This guy is also refractive. Another secondary ray, a reflection ray. This guy is also reflective, right? So now it's sending another ray in this direction. Then I hit this guy, and I hit this guy exactly in the same direction of its normal. It means that now this guy needs to send another ray in the same direction, and now we're just going backwards. The problem is, where do we stop? What do you think? Because we can have an infinite loop, right? If you don't implement this correctly, you can have a specific geometry in which your computer just like stay there forever sending rays, right? And someone is asking, set the limit to the number of secondary rays. Yes, exactly. So that's the thing. We have several options, okay? So historically, people had ideate different options to solve this problem. So one is just keep creating secondary rays until you have no intersection, right? this is a horrible idea, right? Because you might have a geometrical, right? I mean, the geometry of your objects in which in some way in which basically it's just infinite, and you will always have an intersection because they is going just back and forth, and yeah, it will never end. But yeah, but sometimes people, I mean, they used to do this, right? Basically terminate when there's no intersection anymore. Another option that is a bit more realistic, and it's also very expensive, but it's also a bit more realistic, is that if you notice, let me show you this image. If you notice an image like this, it is a ray traced image from the software that you will use for your ray tracing assignment. Basically, the first part of your ray tracing assignment, you will able to render something like this, depending on your computer, in about like 30 minutes, because yeah, this image will take a while in processing in your computer. But the thing is, look at the reflections on this guy. If you see, if you like look very closely, you will see that, for example, the saturation of colors of these objects right here, when they appear on the reflection, they appear a little bit less saturated. So what happens in real life is, unless you're talking about like absolutely perfect reflective material, which basically doesn't exist, right? Not even the most perfect mirror in the world is absolutely perfect. Every material absorbs a little bit of light. So assume that every time you basically are using a material that is reflective, not every light is going to be reflected, right? Because some light is in the end is basically absorbed. It means that the contribution, if I come back to this image, the contribution of this color right here to this object, so this is the first object, right? So this object is basically tracing reflections to decide which will be its ending, its final color. So each time you basically hit a reflective object, you can implement in your code that the contribution for each hit or for each intersection will be decreased, right? So you will basically decreasing the contribution of each color to simulate this thing that happens in real life, that the light is basically losing, right? It's losing energy because every object is basically absorbing a little bit of light, right? So if you do that, the way you're kind of the way you could like maybe like stop your algorithm is by checking if the contribution of those secondary rays is below some threshold, right? So you're every time you hit something new, you're maybe like, imagine, I will just super simplify this. Imagine that every time you're hitting something new, every new secondary ray as reflection ray, you reduce the contribution by, I don't know, by 20%, right? It means that this guy will contribute only 80%, right? And now this guy will contribute 80% to this guy, so its contribution to this guy will be less, right? So basically you keep tracking this. Yeah, the contribution is just getting dimmer, and maybe you decide that once you end up with a very far reflection from which its contribution is, I don't know, maybe less than 5% to the original object, you stop there, right? So that's another way to stop. That is super realistic. That will be, yeah, that will be very very good way to do it, but it's also very expensive. That I as far as I remember, almost nobody used this approach, right? Because yeah, it just gets super expensive. It can get very expensive. So the other way is to define a maximal depth. It's just to define a number. Say, okay, it doesn't matter doesn't matter the contribution. I mean, you still can reduce the contribution, but instead of leaving it, right, as, yeah, maybe sometimes you will hit 2 or 3 rays, and maybe sometimes you can hit 400 rays. You just say, okay, I will set it to a maximal depth. So that has a name, and it's called ray depth. So ray depth is basically the maximum number of secondary rays you allow the computer to process your ray tracing. So if I come back, for example, here to 3 to the max, I can show you the properties. And again, I think Maya, Blender, most softwares, they use this option. So if I go to Ray Tracer, this is the maximum depth. This is the one that you have for default. It's 9, right? So I can obviously increase this, but 9 is the one from default, and yeah, it means that if I apply ray tracing and reflective materials in 3 Studio Max, it will never bounce more than 9 times, right? And actually 9 is actually a very high number, by the way. So this one is basically the most common. Questions about this? Yes. Someone is asking, does this mean that we only get maximum of 9 bounces? Yes, maximum of 9 bounces. It doesn't matter the contribution, because again, the contribution can be super realistic, right? For example, you can also like modify the contribution of every new hit by the distance that the ray is traveling, right? If an object is very close to a reflective material, it will contribute more, because if an object is very far from the material in real life, you have air, right? So for example, I don't know if you notice, if you go outside and see mountains very far from you, you will see the mountains as they're farther from you. You will see the color of the mountains get like bluish, and the very far mountains will get very dimmer, right? The saturation of colors that will be very dimmer. That is because you have a lot of air between you and those mountains, right? So again, the light, the contribution of the light is getting dimmer, right? Yeah, you can have like pollution, dust, and everything, but within that is actually that effect, the effect of when you see an environment in 3D and you simulate that effect, that the objects that are very far, they start to lost their the saturation of the colors. That is called perspective area. Yeah, that's the name of that effect. Perspective area is yes. So yeah, you have a question. Yeah.
Hey, just to clarify, when we talked about the contribution of secondary rays, so the rays basically have strengths associated with them, and the amount of contribution they lose after bounce is a material property, right?
Yes.
Oh, okay.
Yeah.
I guess my intuition is that the more reflective a material is, the less amount of strength the ray loses.
Yes, because absorbs less light, right?
Right.
But again, these things are effects that are in the end are optionals, right? I mean, you don't need to apply everything that we are talking about to your ray tracer, right? But yeah, these are just optional things that can make this the renders look better. Okay, and someone is like, if imagine if CG evolves to a point where rendering becomes more realistic than reality. Well, that is interesting. Since rendering, yeah. And one bounce is okay, and someone was asking, one bounce is one reflective ray light. Yes, exactly. So yeah, this is one bounce, one reflect, right? One reflection, one secondary reflection ray, second bounce, third one. Yeah. Okay, so now let's keep talking. Now let's talk about multiple objects. And by the way, it's almost, I think it's almost, it's 3:49. I think we will have the same problem, that because you're asking too many questions, and I'm not regretting, I love when you're asking questions, but I think we will not have time to finish the lecture, and I really want to finish all the topics today. So yeah, so do you have a problem if I just keep the class, and if it doesn't matter if we pass the hour? Remember, if you really want to, if you really need to go, you can go, and then you just check the video. Okay, so give me a second. What do you mean by, okay, someone is asking, Professor, we can consider pre-class videos. I don't understand your question. What do you mean by we can consider pre-class videos?
Some classes have mandatory videos they have to watch before the lecture, something like that.
Oh, I see. Yeah, I mean, yeah, we could do that also, but yeah. I guess, I mean, today I think it's better to just keep going. Okay, so multiple objects. So let's think about this scene. We have two objects, well, three objects, right? But in the path of my ray, we have two objects. They have non-reflective light. So we will need to iterate these objects, right? And even if we are applying space partition algorithms, I know for sure I will need to basically get these two objects. So the question is, which will be the final core of the pixel? The one from the first intersection or the one from the second intersection? What do you think? Okay, yeah, somebody is already saying depends on the alpha value. Yes, of course, because we can say, oh, maybe the closest object, right? But if this guy is transparent, if this guy has half alpha value, yeah, maybe not. So this is important. When we talk about ray tracing, we usually think of super realistic images, right? So super realistic images, we usually meant that if something is transparent, like this ball right here, we are using refraction, right? Refraction is a very interesting thing in ray tracing, in which I am throwing rays and the rays are basically going inside this object, but depending on the shape of that object, the rays are basically like changing direction, right? So these objects right here, right? You see everything like backwards because these guys are basically mimicking a real like glass sphere, and this is basically refraction. Sorry. So, but the thing is, even in ray tracing, we sometimes use the trick of treating objects as just transparent, right? just getting the alpha value and blend the color of something that is basically transparent, and not necessarily compute the refraction. Refraction it takes a lot of time. It takes a lot of time and it's very expensive. So yeah, if things are transparent, we need another approach, right? Not only to decide the closest object. So what we usually do is something called Z buffering, and this is important because Z buffering or C buffering, it also applies for real-time rendering. We never discussed that when we were talking about the pipeline rendering, because I was just waiting to discuss it here. But in real-time rendering is basically the same. So the rendering pipeline from OpenGL or also DirectX, they also have this technology called depth buffer or set buffer that basically decides which fragment is rendered depending on its depth. I mean, we already discussed that when we were talking about ray tracing. We discussed the depth test. Remember, that is basically a fragment, one of the per fragment operations. But I never told you literally about the set buffer. So what is a set buffer? Basically, when you're computing your scene, what you have. Let me show you this one, for example. What you have is you have two chunks of memory when you're computing your scene. Again, either if you're doing real-time rendering or if you're doing ray tracing, you have two chunks of memory. One is called color buffer, in which you are basically storing, right? It's a 2D array in which you are storing for every ray that you're shooting, you are basically storing the color of that object, right? Oh, sorry, the color of that pixel, right? But it's like a preliminary image. It's not the final image, right? Because maybe you started by computing the colors from the green object right here, right? The green sphere. So the final color in this case will not be exactly green, right? It will be basically a combination between this green and also this guy here, because this guy is not using refraction. This guy is just a fake transparent object that I'm just using its alpha value, right? So you have two chunks of memory. The one that is basically computing like pre-values or optional temporary values for the color. And also you're storing alpha value or depth value. So basically a depth buffer is just a chunk of memory in which you're saving for each intersection you get in your rays, or for each fragment in the case of the real-time rendering technique, you're getting the depth from that for that object in particular, right? So yeah, so that is basically set buffering. And so you get something like this, right? Again, you have two chunks of memory, one in which you're saving the color and the other one is in which you're saving the depth. So whenever you hit with something new, you check its distance, right? So you check the distance from your camera to that intersection. Let's assume that you are sending a ray and you intersect with the sphere. So you check the depth or the distance from the camera to that intersection in particular. And you go and check the depth buffer. If the object is opaque, for example, right? Let's imagine that the object every object is opaque. Let's imagine that you don't have any transparent object whatsoever. Everything is opaque. So you get that intersection, you get that distance, you go to the depth buffer or to the set buffer, and for that pixel in particular, the distance that is stored in the depth buffer is closer from the one that you have already. It means that that intersection that you got, or that fragment in the case of real-time rendering, you need to discard that fragment, right? Because there's something that is closer to the camera that is also opaque, and for sure you need to use that color in particular, right? And it was this the very curious thing about this is that set buffering, or this idea of like having a chunk of memory to store all that depth information, it was considered like a very stupid idea. This was in the middle of 70s, because at the time memory was incredibly expensive. So the first frame buffer that was designed to like deal with this type of things was more than $50,000. It was incredibly expensive. So it was like, yeah, people were doing this type of algorithms saying like, okay, yeah, it's very creative. It's like, oh, nice idea, but it's just impossible to achieve, right? But now everything like memory is just super cheap. So this is the type of thing that we usually do in terms of depth, right? Okay. Okay, questions about depth? Okay, someone was asking, alpha value is transparency? Yes, alpha value is transparency. So it's basically the opposite of opaque or opacity. In some systems, this is important. In some sometimes in certain softwares, they don't call it transparency, they call it opacity, right? So for example, I think 3 to the max it calls opacity. So a 100% opacity, it means that it's blocking 100% of the light. 0% opacity, it means that it's blocking 0% of the light, which means it's transparency. Yeah, so sometimes they use the other name. They use the other name. Okay, someone was asking, so the image on the right is the result of the depth test. Yes, basically this image is a representation of how the depth buffer or the depth memory will look. I mean, it will not look exactly like this while you're processing the image, right? I mean, this is basically the final result after you process everything. But imagine that if you are, for example, rendering maybe you hit this object first, right? So it means that the depth map at the beginning will have everything in black and only this blue, the blue guy with all the depth information from the blue guy. Then you start to render, for example, the red one, and your depth buffer will start to like discard information that is already on the memory because maybe it's hitting something that is it is closer, right? So if you hit now your ray, for example, is hitting this object right here, and you get a depth that is closer to the previous one, the one from the blue, you basically go to your color buffer and you update the color of that pixel, because that pixel before was blue, right? You update the color of your color buffer, and you also update the depth in your depth buffer, right? That is basically the algorithm. But again, this type of things, it's already automatic, and you don't need to in real-time rendering, for example, this is done automatically and you don't need to do anything else. You might need to play a little bit with this with your assignment, but everything is also explained on the book that you will need to follow. Okay, so finally we need to talk about aliasing. Okay, and this is the last part of the lecture today. So aliasing is this. Remember that when we talk about rasterization, right? And again, this I'm kind of going back to real-time rendering. We said that we have a screen, right, with pixels, and we have a triangle like this, and a triangle basically represents a continuous geometry, right? But when doing the rasterization algorithm, or yeah, the rasterization part, we're basically converting from continuous to discrete, right? Because the image is obviously discrete. So this is basically the discrete version of this triangle. And because I have a very poor amount of pixels, this is what I get, right? So this happens in computer graphics. In this object right here, for example, this have this problem called alias or aliasing, right? Which basically means that your information is totally discrete, right? And these objects are basically black. You can see the jaggy borders, right? So an anti-alias is basically a solution, is to come up with a solution to this problem, in which instead of having like the like a flat color for every pixel here, you need to kind of like blend the values from those pixels, right? To make these images a bit more appealing, right? So in some sense, anti-aliasing is something in which you can see the problem as you have a continuous information. Imagine that you have like a continuous curve, right? A continuous function. Then you discretize that information. But when you want to create the final image, you somehow need to like reconstruct the continuous information from the discrete information. So there are different ways to see this problem. One way is to see this problem as an optimization problem, or even you could like apply Fourier analysis, right, to detect, for example, like the non-representative areas from that function. So it could be a very sophisticated solution, or a very tricky solution, which is usually what we do in computer graphics. So these are the three most common solutions for anti-aliasing, for the aliasing problem, or these anti-aliasing techniques. So the first one is called supersampling, which is horrible. That basically this idea is, okay, if I need to create this image, right, that it has, let's imagine that this image has, I don't know, 100 by 100 pixels. And because you have just a tiny amount of pixels, you will have a lot of aliasing and your borders will look very jaggy, right? So one idea is, okay, I will render a higher resolution of my image, so I can render the image 3 times bigger or 4 times bigger, right? And now that I have that image, I just decrease the size of the image, basically averaging the pixel color. So for example, this image is, let's say, twice as big as the original, for every pixel in your final image, you will have 4 pixels on this image. It means that the pixels on the borders, for example, you'll have 4 times more information, right? So you get all those 4, right? All those 4 pixels, you just average the color, and it means that your image on like the smaller version of the image will look better, right? The problem is this is just a very bad idea, right? Because you need to like compute a higher resolution image, so it's not a very good idea. But this was one of the first ideas to solve anti-aliasing, and yeah, I think people were using this maybe on the 90s, right? Something like that. Okay, so the second idea is multisampling, and multisampling is also not as sophisticated, but it's also a good idea. So the thing is, imagine that this is a pixel, right? And for every pixel, we are sending a ray, right? So let's talk about ray tracing. We are sending a ray for every pixel. So that is what we do basically, is to send a ray basically at the center of the pixel. So instead of having a single ray or a single sample from that pixel, we just throw more rays. Instead of sending one exactly on the center, you can just take several samples or take several rays, right, and different positions on that pixel. And there are different algorithms for multisampling anti-aliasing. If you go and Google multi-sampling anti-aliasing, you will see different algorithms. One option is just to throw random points. Actually, the one that is on the one that is on the code that you will use for your ray tracing assignment, it uses just random points. So you can just throw a certain number of random points in your pixel, or sometimes they make them follow a certain pattern. So imagine, for example, in this case in particular, sorry, if we go back here, if I throw, let's imagine that I throw 4 random points. I mean, I have more here, but let's imagine that I throw 4 random points. It means that for every pixel, I will get, let's assume, the one from the center plus 4 more, right? So I'm basically I will need to cast 5 primary rays for every pixel. And the thing is, each of these rays, they need to do exactly the same of the original one, right? For every ray, I need to compute everything. I need to compute the intersections. I need to compute shadow rays. I need to compute reflection rays, depending if you have reflective materials, right? So it will increase your rendering time horrible, right? So in that case, let's assume you're maybe casting 5 rays per pixel, right? So maybe the one on the middle plus 4 in random positions. This idea, for example, is different because in this idea, you have 1 in the middle plus 4, right? 4 new samples. But the way you place your samples is you place the samples to basically collide with the next pixel. So this is a very nice idea because basically for the next pixel, you don't need to compute this one, right? So the first pixel computes 5 points. The next one will need to compute how many? Only 4, right? Because this one is already computed. So once you're basically like going to the next pixels, there are a lot of samples that you're basically already saving because you have that information already. So basically by taking your samples, when you're using multi-sampling, by taking your samples basically on the edge of the pixels, you can basically save the amount of samples that you do. This is one of the things that you can, for example, apply in your assignment because your assignment uses this approach. The coding for your assignment originally it uses this approach, just random samples. You can, for example, try this type of samples to accelerate the process of your ray tracing. Now, here we are still talking about multi-sampling. So basically, what this means is, imagine that we have a sphere, right, and we are casting this ray, and this ray is almost touching is basically the ray that is touching the border of the sphere, right? So getting this different samples, what basically how it looks is, for that pixel in particular, you're just throwing more rays, and for example, one of those rays maybe can hit the sphere, but another one maybe is not hitting the sphere, right? So basically, what will happen is that the border of your sphere will look, like softer, right? Because you're doing this multi-sampling, and it looks really good. Okay, so the other option is doing something called post-process filters. So, for example, Trees2Max, this is what Trees2Max does. I think Maya also does this. I think also Blender. So this is a bit more sophisticated. So in this case, instead of computing multi-samples or sending more rays, because I mean that is expensive, what this option does is once the final image is created, you apply a filter to detect borders on that image. You can use like high pass filters, or there are different filters in computer vision in general that you can apply to detect borders of your image. So basically you identify the borders of the image, like this in this example, and then only for the pixels that are on those borders, you can apply a certain filter. So for example, you can maybe just average the colors, or you can use, I mean, there are a lot of different filters for that thing. I can even show you very quickly. Give me a second, because I have a demo for you. Give me a second. Antialiasing, yes. So let me show you. So for example, here I have a triangle that is is animated, right? So this is a very thin triangle, and I am give me a second. I will render this image with 40 by 36 pixels, right? So let me show you how it looks without anti-aliasing. So this is the image. Okay, I will increase the size. So this is how this triangle looks without anti-aliasing, right? So it looks horrible. And in particular, anti-aliasing is very bad when you see things moving. So let me show you what happens. Look at what happens if I make an animation. Look at this. Basically, I'm rendering, right, this animation, and yeah, basically the edge, right? It seems like stairs, and it seems like they're like crawling, right? That is actually the name that it has. This type of this type of effect, or this type of artifact in computer graphics, we call it like they're like crawling, right? Like the edge is crawling. So please look at what happened if I go to the renderer and I activate the anti-aliasing, right? So this will be, give me a second. This will be the difference. See, it's way softer, right? And in particular, again, this depends on the technology, depends on the many things, even the hardware. So for example, Trees to Max, they don't use multi-sampling, they use post-process filters. And I think Blender, Maya, I think most computer softwares, computer graphics software right now, they use post-processors. And there are a lot of different filters. So you can use area, Blackman, blend. These are just different filters to decide between those pixels that are basically on the border, how to decide which colors they need to, or how you basically blend those colors. And you have parameters also. For example, in the case of area, is the number of pixels outside the original pixel that you are basically like blending that information. So for example, if I increase this to 5, what it's basically doing is it's taking the pixels that are on the border and it's going up to 5 pixels around to basically blend the colors. So it will be super smooth, right? Because you're basically like going up to 5 pixels, yeah, from the border. So yeah, you will have just different result, right? Okay, and yes, and we finished for today. Okay, good. So any question about anti-aliasing? Yes, 2 more lectures until the next midterm. Yes, and I think on the webpage we have a topic before the midterm, but we will probably have a review, right? So yeah, we will definitely have a review before the midterm, and it will be as the previous review. We will start at 3 p.m. and I will just keep going and going and going. And if you have questions, I will just answer every single question. If we spend 2 hours or 3 hours in the review, I don't care. As long as I have students asking, I will just keep answering questions. So that will be before the midterm. Why do we need the anti-aliasing? Well, because this effect I was showing you, right? So let me just go back. So this doesn't look that bad, right? So look at for example, the animation will not look as bad. I mean, it still crawls a little bit, right? But basically, you can see here that. Give me a second. This like the different colors on the edge of this object, right? They're not like either totally purple or either totally white, right? It means that this is, I mean, it is still discrete, but we are kind of reconstructing the continuous information, right? because otherwise, if I don't apply the anti-aliasing, I just get the discrete version, right? Which looks horrible, right? And I have actually a last comment about anti-aliasing. Again, so there are different types of anti-aliasing techniques. This depends a lot in hardware, different technologies, and so it's also, yeah, it's also very complicated. There are a lot of papers. There are a lot of, every company, Nvidia is always trying to like improve their anti-aliasing techniques. Sometimes they're like very embedded in their algorithm, sorry, in their hardwire, right, in their things. But for example, their Apple, for example, Apple, they don't have any anti-aliasing algorithm. They don't apply any anti-aliasing algorithm. That is very interesting. And however, I mean, you can play something in your iPhone or iPad and it looks perfectly fine. So what Apple does, for example, is instead of worrying about anti-aliasing, the aliasing problem, sorry, and apply some anti-aliasing sophisticated algorithm, the Retina display from Apple, I guess you know that you've heard about that technology, right? I guess, I think as far as I remember, every single product right now, every Apple product has Retina display. So the Retina display technology, what they do is they made the pixels so tiny that your eyes, basically your eyes are it's impossible for your eyes to see individual pixels because they're super tiny. So you can have, just so the images, you can have images without any anti-aliasing. So basically you can have aliasing images, but you will never notice this like jaggy artifacts because just the pixels are just super small. So the Retina display, for example, is yeah, they just like packed more pixels in the same area, and is, yeah, it's just impossible to see the problem. And so that's another solution, right? Not using anti-aliasing, because now it turns out that you have just a lot of pixels. Okay, so if you don't have any more questions, I think it's we can end up here for today, and I will see you on Friday, right? Because we don't have, oh yeah, it's Remembrance Day on Wednesday, so I think I see you until Friday, right? Okay, see you everybody. Bye. Have a nice holiday.